All right, guys. Hey, welcome back to another lesson. This will be Optimization with Linear Programming Part 2, okay? Part 1 was just looking at the function and the restrictions given to us, and then we had to graph the restrictions, find the critical points, plug them into the function, and figure out if there's a max or min involved, okay? Today, we're actually going to do everything from scratch. We're going to come up with the restrictions, come up with the function that's going to be optimized, finding max and min, and graphing it and all that stuff. So let's take a look. So right here, if you're a person who likes things written out in steps, this is the steps that you can take to solving these guys. First, define your variables. It doesn't have to always be X and Y. I want to be very clear with that. You can use other variables to represent things. It just depends on the problem, and you'll see that in this example coming up. Write a system of inequalities, graph the system of inequalities, find those critical points, that's the feasible region, write a linear function that's going to be optimized, max or min, substitute them into the function, and then find the result, okay? Figure out what it is. Now, real quick, just to, is this going to work? No, it's not. Okay, I'll just tell you anyway. Looking at looking at step number 5, I include that in step 2. I just write all the equations out, but once again, I mean, it's not a big deal if you don't, okay? So let's go ahead and we're gonna take a look at the first problem here. So landscaping, okay? A landscaping company has crews who mow lawns and prune shrubbery. The company schedules 1 hour for mowing jobs and 3 hours for pruning jobs. Each crew is scheduled for no more than 2 pruning jobs per day. Each crew's schedule is set up for a maximum of 9 hours per day. On the average, the charge for mowing a lawn is $40 and the charge for pruning shrubbery is $120. Find a combination of mowing lawns and pruning shrubs that will maximize the income the company receives per day from one of its crews. Now, I don't know about you, but if I was in high school and I read that problem, I would think information overload, right? Like, where do I start? How do I even think about solving this guy, okay? And here's how, this is what it just comes down to. When you're doing this, don't panic, okay? Pick out certain things in the problem and just look at one thing at a time. Don't look at the whole picture yet, okay? And that's what we're gonna do. We're just gonna look at things up, one at a time, and then we'll look at the whole picture, okay? So what I'm gonna do, let me just move this around here. There we go. Oh no, that little, there we go. Okay, and, oops, sorry about that. I don't know why that did that. Okay, so here we go. So let's just read through this. Now notice, the first thing that pops to my mind is there's a time frame for mowing and pruning jobs, right? We have 1 hour for mowing and 3 hours for pruning jobs. And that's all we're really talking about in this whole problem is those two things. So I'm gonna say M is gonna represent mowing, that variable, and P is gonna represent pruning. How original, right? So those are gonna be my variables, okay? Now, for the next part, I need to come up with some inequalities, some restrictions, right? So let's see. It says here that the maximum hours per day that the crew is allowed to work is 9. Okay, so let's think about that for a second. I could write down that it takes 1 hour for mowing plus 3 hours for pruning, okay? And that has to be less than or equal to 9. Now, because I'm typing this out, there's no symbol for that, so I apologize. So you're gonna have to just bear with me when it comes to the symbols here. So we have one equation, so this is the hours. That's what that represents, that restriction, okay? So notice, that's less to look through in the problem, right? We created an inequality about the hours. Okay, now let's see about another one here. Each crew is scheduled for no more than 2 pruning jobs per day. Okay, let's translate that. So pruning is P, right? So pruning jobs has to be less than or equal to 2. Okay, once again, I can't go past 2, so it has to be less than that, or equal to. I'm allowed to have at least 2. All right, that one's gone. Now let's continue reading on. The charge for mowing a lawn is $40 and pruning is $120, and they want to maximize the income. Okay, so that to me sounds like a separate, that's like a function we're talking about there that we're trying to optimize. So for right now, just taking a look at what we have our two variables. We have one for hours and one for the max number of pruning jobs, okay? So we have all this stuff. Now you could have one more restriction, it's up to you. I think it's kind of implied, but we should probably include it. The pruning and mowing jobs has to be greater than or equal to 0. You can't have negative jobs, right? So let's include it. It'll be good to include that there, okay? All right, now, the function that's gonna be maximized. So I'm gonna call it function f. No reason why, just that's a common. And I'll put m and p. Those are my two variables I'm using. So it takes $40 for every mowing job plus $120 for every pruning job, okay? So this is the thing that we're trying to max and min. That's what that equation stands for, okay? Now, when we graph this, we're only graphing the restrictions because that's going to tell me specifically what numbers I'm allowed to plug into that function f, okay? And then the critical points is what we're going to pick to see what function f's max and min is, all right? So I'm going to stop sharing the screen. You're going to look at the board here. So let's do that right now. Hey, how's it going? All right, so here it is. Now notice, and let me pick a color that you can see. I'm going to choose just a black marker here so you can see it a little bit better. I chose M, the mowing jobs, to be the x-axis and pruning jobs to be the y. Now here's the deal. You could flip these, okay? You can make an argument, you know, as to like independent, dependent variable for each side. So in this case, it doesn't really matter. Now I will say your graph is going to look a little bit different and your critical points are going to be switched, all right? They're going to switch places, your x and y coordinates. But you're going to get to the same conclusion, and I want to be very clear on that, okay? So if you do graph a little bit differently, you're still going to come up to the same results, all right? Now, what I'm going to do is I'm going to take these guys, my restrictions, I'm going to graph them. So this one right here, we'll start with this. This is the easiest. This says p is less than or equal to 2. That's going to be a horizontal line at 2, okay? So I'm going to try my best. Okay, so there is that guy graphed for us. All right, now this is done. Now m is greater than or equal to 0, p is greater than or equal to 0. That is literally the axes of this grid. So technically I have nothing to draw there. That's why I said it's not that that's not important to state, but it doesn't really add anything to the graph because it's technically there already. Okay, this guy right here, this troublemaker, okay? I'm not using x and y anymore, I'm using p and m. So what you want to do, my y is technically the variable p. So I'm going to solve this for that, okay? So down here, I'm going to write 3p is less than or equal to negative 1m plus 9. And then my last step is to solve for p. So p is less than or equal to negative 1/3 m plus 3. So I'm going to graph this line, okay? So I'm going to start here at 3, 1, 2, 3, okay? And then what I'm going to do is I'm going to go, what, down 1 over 3, 1, 2, 3. And then once again, down 1 over 3, 1, 2, 3. Down 1 over 1, 2, 3. Okay? And I'm going to draw my line. Now this is a hand-drawn graph, so it might not look exactly symmetrical, but I'll tell you what points are truly there for accuracy, okay? So you're gonna notice that when I shade, well actually let's talk about shading. This says I want to shade below the horizontal line. This one says I want to shade below the diagonal line. So what that looks like is it's this little trapezoid region. It's all my solutions, okay, for this guy. So my critical points are where the shaded region is and where those lines intersect. It has to include both of them. So notice this guy right here, which is 0, 2. Excuse me, that's one of my critical points. This here at 0, 0, another critical point. But to be honest with you, that one is probably not going to maximize anything. But I'm still going to write it down. This point right here would be 3, 2. It's another critical point. And the last one out here is going to be 9, 0. Okay, so those are going to be my critical points for that guy. All right. Okay, so let me, that's all graphed. Use a different color marker here. So what I'm going to do, I know what my function is, right? Okay, and I'll write this down again so I have it on my paper now. Where is, there it is. Okay. So the function of this guy was what? 40m plus 120p. Okay. So I have my points here, and then we'll have my outcome. Okay. So there we go. The points that I have would be 0, 0, 0, 2, 3, 2, 9, 0. Now, once again, if you flip these, your graph will look different, and really you're going to be flipping the coordinates here. All right. Doesn't mean you're wrong, though. All right, I'm going to plug these in. So this is 0. I'm not going to bother with that. Okay, so really that's probably not going to be a max or a min for you. It could be a min, we'll see. This one would be 40 times 0 plus 120 times 2. Okay. And then we got 40 times 3 plus 120 times 2, 40 times 9 plus 120 times 0. Okay. So far, so good. So now what we're going to do is simplify. So this would be $240. And 120 would be this guy. This would be 240. So that's $360 for this. And that's $360 for this guy. Okay. So notice something. We have two maximums here, huh? We certainly do. It's these guys right here. Two maximum values. And that could happen. So what that tells me, let's interpret this. So 3, 2 is a maximum. So what that means is you can have 3 mowing jobs, 2 pruning jobs. That'll give you the maximum amount of money for that day's work, which would be $360. Or you can do 9 mowing jobs and 0 pruning jobs and get the same result, which is their maximum of $360. Okay? If you don't do any jobs that day, that's your minimum. Okay, you're not going to earn anything. So there is a minimum here, but it doesn't really help us in terms of analyzing this function. Okay? So there's my answer for that guy. Any questions, thoughts, concerns, dilemmas? Are you marveling at this wonderful graph that I just drew? Not bad, honestly, for a hand-drawn graph. I don't think so. Okay, you ready for the magic here? You ready to see me erase this carefully? Because I want to use the same grid again. Here we go. Get rid of this. And one thing to note, I shouldn't erase that, but that function we created, remember, we're never graphing that, okay? That function's being optimized. The solutions that we're seeing in here is what we're allowed to plug into that function, okay? But the critical points, specifically, we want to use because they give me the max or min, okay? The other solutions that are in this shaded region are going to fall between that. So between 0 and 360, all these solutions will tell you how much money you're getting. You won't get past 360, and you're not going to get negative money unless you break down, right? If your equipment breaks down, you could be out for some money. So, but that's another restriction. That's another variable which you could add to this. really good. Okay, enough talking. And more erasing. Okay, I think that's good. Yeah, I got a couple points here, but we'll leave it there for right now. Okay, so zoom back up here. Hey, how's it going? We're gonna go ahead and go back to the PowerPoint. Ta-da! And we're gonna try another example out. I'll show you too, like here's what the graph looks like if you want a larger picture of it. You can see all the critical points there that we found, okay? All right, so let's go ahead and figure out this guy here. Another landscaping type of job, and I encourage you, pause the video and try this out for yourself. So let me, oh, no. Let's move this upside some room, text box, boom. Okay, so it says here, a landscaping company has crews who rake leaves and mulch. The company schedules 2 hours for mulching jobs, 4 hours for raking jobs. Each crew is scheduled for no more than 2 raking jobs per day. Each crew's schedule is set up for a maximum of 8 hours per day. On the average, the charge for raking a lawn is $50. The charge for mulching is $30. Find the combination of raking and mulching that will maximize the income and the company receives for one of its crews. Okay. I like these problems. I really do. I think it shows you a lot of great application, especially for those of you if you want to start your own business, some numbers and some graphing that can help you maximize your profit. So here's something original. R is going to represent raking jobs, and M will represent mulching jobs, okay? You could use X and Y. I'm not going to, downplay those variables, but they use so much. Why not try some new letters out? Okay, let's talk about restrictions. So let's go through this. Let's talk about hours. We're only allowed 8 hours per day, okay? So that's an inequality I'm thinking about. And let's go ahead. So it's 2 hours for every 2 hours for every mulching job, okay? Plus 4 hours for every raking job, has to be less than or equal to 8. Okay, I can't go past that at all. Once again, apologize. It looks like a smiley face, doesn't it? It actually does. It's amusing. All right, next I'm gonna come up with another inequality. Well, if I'm reading this correctly, I'm not allowed to have more than 2 raking jobs per day, okay? Not sure why, and I think you can kind of see it because raking jobs take the most hours, right? So you can't do more than 2 because that's more than 8 hours you're allowed per day. So there's a reason why for that. But anyway, raking jobs would have to be less than or equal to 2, all right? I'm also gonna include the obvious that you can't go negative with the mulching and raking jobs. So those variables have to be greater than or equal to 0. They look like frowny faces, to be honest with you, right there. Or if you look at the other direction, they look like mad faces with their mouth open. Trying to give you some humor here. Okay, now those are the restrictions. Now it wants us to maximize the income. So already I'm thinking, okay, that's the function I need to write down. Not the one I'm graphing, but one that I'm going to plug my critical points in. So here we go. I'm going to write this up here. So my function has the variable R and M in it. Okay. And I'm calling it function F. You can call it any function you want, G, H, you can pick. Okay. In fact, you know what? F gets used a lot. Let's call this function I for income. How original. Okay, so we have here that raking a lawn is $50 for every one of those jobs. And mulching is $30 for every one of those jobs. Okay, so this is the equation we want the max or min from. Okay, not the one I'm graphing, but the one that I'm going to plug my points into. Okay, so let's go ahead and graph this. So I'm going to stop sharing. Hey, welcome back. And here is that lovely graph that I tried to preserve from the last one. Okay, so I'm now going to make this guy M for mulching and this one R for the raking jobs. Once again, it doesn't matter what it is in this case. Your graphs will look a little bit different. Okay, and in fact, I'll show you a picture of it when we're done, what it could look like here. So I know this criteria, they have to be greater than or equal to 0, which is the axis already here, so that doesn't add anything more to the graph. Okay. So next is the hours you're allowed to work, which is 8. Okay, and this represents how many hours per job. And we can't go past this guy right here. Can't go past 2 regular jobs. Okay. I think that's it. Alrighty, here we go. Let's graph. This one ain't too bad. So the first one I want to graph is this guy. Now this, because it's an R, that's going to be a vertical line, right? And here's an easy way, because now we're not dealing with X's and Y's anymore. There's no M's in this, right? So remember, I want to draw a line that doesn't hit the M axis. That has to be a vertical line. So let's go where 2 is. And let's draw a nice vertical line. It goes right through 2. There we go. Okay, there's a restriction there. Now for the other one. Now remember what I did before? I solved for a variable and I started plotting it like slope-intercept form. Do the same thing here. So let me bring this down. Because M is technically my new Y value, I'm going to solve for M. So here we have 4R less than or equal to negative 2M plus 8. Divide everything by 4. R is less than or equal to negative 1/2 M plus 2. So this is something that I'm going to graph here. Okay? What do you think? So far, so good? Oh, I didn't solve for M, did I? I solved for R. That would have been trouble for me, to be honest with you, because I situated everything for the other variable. So I apologize. Error. So it'd be 2M less than or equal to negative 4R plus 8. If I divide everything by 2, I get negative 2 plus 4. Sorry about that. That could have been bad. And the only reason why I say that is because I already established that R is the X and M was the Y. Okay, so just be careful when you actually are graphing these, that you don't flip-flop during it like I almost did. So I'm going to start here at 4. 1, 2, 3, 4. And it's negative 2. So down 2 over 1, down 2 over 1. There we go. And that's all, technically, that's all you really need the points for, is just to see where they intersect. Okay, just like that. It just helps. I got a critical point here at 0, 4. And it looks like I got another critical point here at 2, 0. Now, is 0, 0 involved? Well, here's where we have to be careful. And I should have did this first. I apologize. They want me to shade underneath, right? Less than. And this one says the same thing, shade underneath. So when I do that, shade to the left and underneath it, this little triangle region is where all those answers are. So yeah, I am going to include 0, 0 in this group. No, you're not dismissed. Just because you hear the bell, you can't turn the video off. You can't walk away. We're almost done, I promise you. Okay, just hang on. So here are my 3 critical points. Okay, and what I'm going to do is plug them into my function. And we already named our function. We call it I. Here's my 2 variables. In fact, I'm gonna shrink that line there because I'm running out of space. So we have 50R plus 30M. So here's the points I'm gonna list, and then here's the outcome. Okay. So 0, 0, 0, 4, 2, 0. Now, because we want to maximize, just like the previous problem, I shouldn't really have to include 0, 0, but it's good to list because here's the deal. Are you always going to have a problem that says maximize? You might have one that says minimize. So I don't want to exclude 0, 0, and then you need it in a different problem. So I'm still going to list it. So this is still going to be 0, output 0. For the next one, we get 50, okay, times. Now, just be careful. Remember, my R value is this guy. So it's going to be 0 plus 30 times 4. Okay, so depending on what your X and Y value is, Make sure you substitute those correctly. Okay, so there's a couple things that could, trip you up. So just be careful. And then this guy would be what? 50 times 2 plus 30 times 0. There we go. Okay. The first one, we get, what, 120? And then for the last one, we get, what, 100 bucks? Okay. So it looks like this right here is going to be the maximum amount of money I can earn in one day. Okay. So let's interpret that result. So 0, 4, okay, and 4 represents the M values, right? So if you do 4 mulching jobs, you will receive the max profit of $120, okay? Now, here's a good question. If this is my company that I was starting up, that's not telling me that pruning is, or not pruning, I'm thinking of the previous problem, that raking is a good thing for me right now. Because raking takes so much longer, it's not really benefiting the company that much. So that's one thing to consider if I was making this, that maybe I can change the tools that I'm using, or maybe hire an extra person so that way I can decrease the amount of time it takes to do a raking job, okay? Because right now it takes, what, 4 hours? And that's kind of killing you here, because if you want the most money per day, right now you need to do the mulching jobs, right? So it's one of those things where you want to take that into consideration when you're thinking about this. What could you do to maximize things? Because if I do 2 raking jobs, yeah, it's $100, but each raking job takes, what, 4 hours? I only have 8 hours to work with, so that's not getting me anywhere, okay? So it's pretty interesting to see, how this really does help you in the real world, like just plotting out those points and stuff. But I like this. This is really cool mathematics, I believe. In my opinion, my professional opinion. Hope you guys are doing well. I really do. If you have any questions, just feel free to contact me. I'll be uploading some practice in the next couple of days. But until the next video, guys, have a good one.